These are the notes on solution stoichiometry. It'll be helpful to have a periodic table available as we will be doing stoichiometry and a calculator. So solution stoichiometry, really we are just combining what we know about solutions with what we know about chemical reactions and stoichiometry. In the past, when we've been dealing with solutions, we've just been looking at, or you've just been calculating the moles of your solute from a measured out mass. Or I've been telling you how many grams of that solute is there. Now you might need to use a concentration and a volume to find moles of your solute. And so using that molarity formula to find moles in a chemical reaction. We're also going to have stoichiometry. Once we have moles, we can go between our different chemicals in our reaction. And then we also are going to be using our writing reactions skills. So balancing, naming, and your solubility rules. The solubility information is generally provided for us, but we can only use our molarity formula on aqueous solutions, and so that's where that comes into play. So let's go through and do an example. I already have the reaction for us. 175 milliliters of 1.5 molar ammonium phosphate reacts with 0.4 molar solution of barium chloride. How many milliliters of barium chloride are needed for this reaction? As we are looking at these, we're going to kind of bounce back and forth between molarity calculations and stoichiometry. With stoichiometry, we need moles or grams in order to do stoichiometry because we know that our number of moles of A equals our number of moles of B for our mole ratio. We also know that 1 mole of some chemical is going to equal the molar mass of that chemical in grams. And so we need either grams or moles in order to do stoichiometry. So we're going to kind of bounce back and forth. Do I need to use my molarity formula to get moles? Once I have moles, I can do stoich. And then if I need something, I can go back to my molarity formula. So looking at what we have, staying organized, we have our balanced reaction. 175 milliliters of 1.5 molar ammonium phosphate. Well, here's my ammonium phosphate. As I look at this, I'm going to kind of write that down. And my first step is going to be that if I have this information, I have 175 milliliters and 1.50 molar. Well, I have enough information that I can find my moles in that case. So step 1 is going to be that we can find our moles. Looking at what else we have, this is reacting with a 0.4 molar solution of barium chloride. And so we have information about this barium chloride. Our barium chloride is 0.40 molar. How many milliliters of barium chloride? So we're looking for milliliters of barium chloride. So we somehow need to get from ammonium phosphate to that barium chloride in our calculations. So in order to do this, our first step is going to be to find moles from the solution that we're given. Molarity is moles divided by liters. So if I rearrange this to have moles by itself, moles is going to be molarity times liters. Moles, is going to be molarity times liters. So we've got 1.50 molar times, well, I don't want milliliters here, so let's go ahead and convert that. Decimal is right here, so 1, 2, 3. So we're going to have 0.175 liters as our volume. 0.175 liters, and that gives us 0.2625 moles of our ammonium phosphate. And I want to do kind of all my sig figs at the end, so I'm going to kind of keep a few digits past my sig figs. But now that I have my moles of ammonium phosphate, Now I can go from, in step 2, I can do that moles of ammonium phosphate to finding how many moles of barium chloride I need. Because once I can find how many moles of my barium chloride, then I can go ahead and use the molarity is moles per liters to find my volume. So our next step then is going to be in that step 2, find our moles of barium chloride, because then we will have our molarity and our moles, and we can calculate liters. So we've got that 0.2625 moles of ammonium phosphate. Well, how do I go from moles of ammonium phosphate to moles of barium chloride? I'm going to use my coefficients from my balanced reaction. So 3 moles of barium chloride to 2 moles of ammonium phosphate, and I can go ahead and do that math. I get 0.39375 moles of BaCl2. And I'm going to leave a couple more digits than sig figs, just because I'm going to do all my calculations at the end, because notice we're just doing multiplying and dividing the whole way through. And so for that step 3, now let's find our milliliters of that barium chloride. So molarity is moles divided by liters. If we rearrange this formula, liters is moles divided by molarity. We know our moles from what we just calculated down here. Our molarity was given to us in our problem. And so my liters is going to be 0.39375 moles divided by that 0.40 molar. And then as we go through and do that calculation, as I look at my kind of sig figs, I have 2 sig figs here, 3 sig figs here. So 2 sig figs is going to be our least amount of sig figs that from what we started with. So I have 0.98 liters. Our question does ask for milliliters, and so 0.98 liters to milliliters, we move our decimal 1, 2, 3. We're going to have we're going to have 980, no decimal, milliliters as our answer. So there is a lot, again, that is happening. We are just kind of adding a molarity formula calculation at the start and potentially at the end of our problem. All right, on to this next one. Feel free to write the formula on your own. I went ahead and wrote my formula before starting this video. How many liters of potassium, of 0.57 molar potassium sulfate solution are needed to react with 85 milliliters of 0.37 molar sodium fluoride solution? So as we're looking at this, we are looking for liters of potassium sulfate. So here's our potassium sulfate right here. So I'm looking for liters. I know that that molarity is 0.57 molar. So if I can find moles, then I will be able to use my molarity and moles to find liters. So that's going to be my last step. Are needed to react with 85 milliliters of 0.37 molar sodium fluoride. Here's my sodium fluoride. So with this, I know that I have 85 milliliters. It's going to be more helpful for us to have liters, so I'm going to just go ahead and convert this. Move 1, 2, 3. So we've got 0.0850 liters, and this is a 0.37 molar solution. And so I'm going to be able to use that to find out how many moles of sodium fluoride I have. Because in order to do stoichiometry, we either need moles or grams. It's going to be easiest for me to go to moles. So to get from sodium fluoride to potassium sulfate, I need to get to moles. So my first step, step 1, is going to be to find moles. And because molarity is moles per liter, moles is molarity times liters. So we can go ahead and multiply 0.37 molar times 0.850 liters. And I get 0.03145 moles of sodium fluoride. My step 2 now that I have something I can do stoichiometry with, is going to be to do that stoich to go from my moles of NaF to my moles of K2SO4. So taking my 0.03145 moles that I just calculated, and I need to use that mole ratio. So we've got 2 moles of NaF to 1 mole of potassium sulfate, and so that's going to give me 0.15725 moles of my potassium sulfate. And again, I'm not going to do sig figs till the very end, so kind of keeping that in your calculator, writing a few digits down past that. And now we've found this value of moles for our potassium sulfate, and so I can then lastly find my volume. So I can find my liters given that molarity relationship. And again, if we rearrange this formula, liters and molarity are going to switch. So liters is moles divided by molarity. So we've got 0.1572, oops, I think I forgot a 0 in here. Apologies, I'll fix that. We've got another 0 in here. There we go. Which means we've got another 0 here. So that is 0.015725 moles divided by that molarity that was given to us, 0.57 molar, to find my liters. I do that division, and then I get 0.028 liters. Go back to your original information on your sig figs. This is liters of our K2SO4 solution. You are going to go back to your kind of original things you were given: 2 sig figs, 3 sig figs, 2 sig figs. You are going to go back to the original things that you're given to look at your sig figs: 2 sig figs, 3 sig figs, 2 sig figs, to end up with our 2 sig figs here. All right. Example 3, here is the setup. This one, you do not have to do a conversion at the end, but you are going to go all the way from moles to grams. So that does give you something that's a little different. Feel free to pause the video and take a look at my work. Example 4 is similar, but it does go back to limiting reactants. And so once you find moles for your solution, then you are going to need to do 2 mole to gram conversions. And again, when we look at those final values, the most we can make is whichever is smaller, because that is our limiting reactant. Reach out to your teacher with any questions.